Welcome to this problem walkthrough. Today, we'll explore problem number 1125, titled Smallest Sufficient Team. This is a fascinating optimization problem where we aim to form the smallest team that collectively possesses all required skills. We'll examine the problem, break it down, and review efficient approaches to solve it. Let's dive in. In this problem, we need to form the smallest sufficient team to cover a set of required skills. The input consists of two parts. First, a list called REQ_skills, which includes all the skills that must be covered, and second, a 2D list called people, where each entry represents the skills that a specific person possesses. The goal is to identify the smallest subset of people such that every skill in REQ_skills is covered by at least one person on the team. It's important to note that if there are multiple valid solutions with the same size, any of them can be returned. The input format specifies that the REQ_skills list will have up to 16 skills, and the people list can contain up to 60 entries. This ensures that the problem size remains manageable. The output should be a list of indices, representing the selected individuals who form the team, and the order of these indices does not matter. For example, consider the input where REQ_skills is Java, Notages, Reactjes, and the people list is Java, Notages, Reactjes. Here, person 0 has the skill Java, person 1 has Notages, and person 2 has both Notages and Reactjes. The smallest sufficient team in this case consists of person 0 and person 2, because together they cover all the required skills. The output for this example is 0, 2. This demonstrates how we select the smallest set of individuals who collectively fulfill all the skill requirements. In another example, suppose REQ_skills is algorithms, math, Java, Reactjes, Sharp, AWS, and the people list contains multiple individuals with overlapping skills. Specifically, person 1 has algorithms, math, and Reactjes, while person 2 has Java, Sharp, and AWS. Together, these two individuals cover all 6 required skills, making them a sufficient team. Since no smaller team can achieve this, the output is 1, 2. This highlights the importance of selecting individuals who maximize coverage while minimizing team size. There are several edge cases to consider. For instance, if there is only one skill and one person who has it, the output is simply that person's index, such as 0. If every person has unique, non-overlapping skills, the team must include all individuals. On the other hand, if one person happens to possess all the required skills, that person alone forms the sufficient team. Finally, when multiple smallest sufficient teams exist, any of them is acceptable as a valid solution. These constraints and edge cases ensure the problem is well defined and provide clarity on how to handle different scenarios. To solve the problem of finding the smallest sufficient team, we explored several approaches. First, there's the brute force method. The intuition here is straightforward: generate all possible subsets of people and check which ones cover all the required skills. Among these, the smallest valid subset is our solution. While this approach is simple and intuitive, it's computationally expensive because the number of subsets grows exponentially with the number of people, giving it a time complexity of 2 to the power of m*n, where m is the number of people and n is the number of skills. This makes the brute force method impractical for large inputs. Another option is to use dynamic programming with bit masking. In this approach, we represent skill sets as binary states and use a dynamic programming table to track the minimum team required for each combination of skills. For implementation, we define a DP array where each entry corresponds to a skill mask. For example, DP mask gives the smallest team that can cover the skills represented by that mask. We start with DP 0, which represents no skills and an empty team. For each person, we update the DP values by combining their skills with existing masks using a bitwise OR operation. This ensures we systematically build up solutions for all possible skill combinations. The dynamic programming approach with bit masking significantly improves efficiency. Its time complexity is n*2 to the power of s, where n is the number of people and s is the number of required skills. While not ideal for very large skill sets due to the 2 to the power of s factor, it's far more efficient than brute force for inputs of moderate size. Compared to brute force, this method is computationally feasible for most practical scenarios. Another approach we considered is the greedy method. The intuition here is to iteratively select the person who contributes the most uncovered skills. We maintain a set of uncovered skills and repeatedly choose the individual who fills the largest gap until all skills are covered. This approach has a time complexity of O(n*(s), making it faster than both brute force and dynamic programming. However, it lacks global optimality and may not yield the smallest team. Ultimately, we chose the dynamic programming with bit masking approach. It offers a balance between efficiency and optimality, as it guarantees the smallest team while being faster than brute force. The greedy method, while faster, doesn't meet the problem's requirement of finding the smallest possible team. Several key observations guided our decision to use dynamic programming with bit masking. First, the problem boils down to a subset selection challenge. We need to cover all required skills using the minimum number of people. Representing skill sets as binary masks allows us to efficiently handle and compare subsets of skills. For example, a skill set can be represented as a binary number where each bit indicates whether a specific skill is covered. This makes it easy to combine skill sets using bitwise operations. Additionally, dynamic programming ensures that all combinations are considered systematically. By storing intermediate results in the DP array, we avoid redundant computations, which is a significant improvement over brute force. These factors contribute to the optimality and efficiency of the solution. We chose this approach because it guarantees the smallest team, unlike the greedy method, which sacrifices accuracy for speed. While the dynamic programming approach isn't as fast as greedy, it's significantly more scalable and efficient than brute force, making it the most suitable option for this problem. In comparing the approaches, the trade-offs become clear. The brute force method, while conceptually simple, is computationally infeasible for larger inputs due to its exponential growth in runtime. Dynamic programming, on the other hand, drastically reduces redundant calculations by storing intermediate results in the DP array. This makes it far more efficient than brute force. Compared to the greedy approach, dynamic programming is slower but ensures optimality, whereas greedy trades precision for speed by not guaranteeing the smallest team. The complexity of the dynamic programming approach, n*(2 to the power of s, is manageable for small to medium values of s, for example, when s is 16 or less. However, for very large skill sets, additional optimizations may be needed to keep the approach practical. Overall, the dynamic programming with bit masking technique strikes a balance between efficiency and accuracy, making it the ideal choice for solving this problem. It provides a systematic, scalable solution that ensures we achieve the smallest sufficient team while handling moderately large constraints effectively. To solve this problem, we aim to determine the smallest sufficient team that collectively possesses all the required skills. Each person in the pool has a unique subset of skills, and our objective is to select the minimum number of people to ensure every required skill is covered. This involves balancing efficiency and completeness. The approach we use is a combination of bitmask dynamic programming and backtracking, which is particularly suited for problems involving subsets and optimization. First, we represent skills using bitmasks. Each skill is assigned a unique index, and a person's skill set is represented as a bitmask, where each bit corresponds to a skill. If a person has a particular skill, the respective bit is set to 1. For example, if there are 3 skills and a person has the first and third skills, their bitmask is 101 in binary, or 5 in decimal. This compact representation allows us to perform efficient operations like union and subset checks. Once we have this representation, the next step is pre-processing. This involves converting the input data into bitmask form for the people's skills and computing the target bitmask that represents all required skills. For instance, if there are 3 skills, the target bitmask is 111 in binary, or 7 in decimal. This target will guide us in constructing our solution efficiently. After pre-processing, we initialize a dynamic programming table to systematically build our solution. This table is implemented as a dictionary called DP, where each key is a bitmask representing the set of skills covered so far, and the value is the minimal team, represented as a list of indices, that covers those skills. Initially, we start with DP 0 equals, which indicates that no skills are covered and no team members are selected. Next, we iteratively update the DP table for each person. For a given person, we compute their skill bitmask, which represents the skills they possess. Then, for each existing state in the DP table, we calculate the new state if this person is added to the team. This is done by performing a bitwise OR operation between the current skill set and the person's skill set, resulting in a new bitmask. If this new bitmask either does not exist in the DP table or represents a smaller team than the current entry, we update the table to include this new state. By doing so, we ensure that only the minimal team for each skill subset is retained in the DP table. Finally, once all people have been processed, the target bitmask, which represents all required skills, will contain the smallest sufficient team in the DP table. We simply extract this team and return it as the result. There are key concepts that make this approach both efficient and effective. The first is the use of bitmask representation. This allows us to compactly represent subsets of skills, making operations like combining skill sets simple and fast using bitwise OR. The dynamic programming table is another critical component. It tracks the minimal team for each subset of skills, ensuring we avoid redundant computations. By incrementally updating the table for each person's skills, we ensure that all possible team combinations are considered. Additionally, the algorithm employs early pruning. Since the DP table retains only the smallest team for each skill subset, larger teams that are not optimal are discarded immediately, saving computational resources. The main data structures used include bitmasks, which are integers representing subsets of skills, a dictionary for the DP table, mapping skill subsets to their minimal teams, and lists of lists to store the indices of team members for each subset. Key operations include the bitwise OR for combining skill sets, subset checks, and team size comparisons, all of which contribute to the overall efficiency of the algorithm. Let's analyze the complexity of this approach. Suppose there are n people and m required skills. The number of possible skill subsets is at most 2*m, which corresponds to all potential combinations of skills. For each person, we may update up to 2*m states in the DP table. Therefore, the total time complexity is O, n * 2 to the power of m. While this may seem exponential with respect to the number of skills, it is efficient given that m is typically small in practice. To better understand how the algorithm works, consider an example. Suppose the required skills are Java, Python, and SQL, and we have 3 people with the following skills: the first person knows Java, the second knows Python, and the third knows both Java and SQL. Our goal is to select the smallest team that collectively possesses all 3 skills. To execute the algorithm, we first map the skills to indices, such as Java to 0, Python to 1, and SQL to 2. Next, we compute the bitmasks for each person. The first person, knowing only Java, has a bitmask of 001 in binary, or 1 in decimal. The second person, with Python, has a bitmask of 010, or 2 in decimal. The third person, with Java and SQL, has a bitmask of 101, or 5 in decimal. The target bitmask, representing all 3 skills, is 111 in binary, or 7 in decimal. We then initialize the DP table with DP 0 equals, meaning no skills are covered and no team members are selected. As we process each person, we update the DP table. Adding the first person results in DP 1 equals 1. Adding the second person creates DP 2 equals 2. Adding the third person updates 2 entries, DP 5 equals 3, and DP 7 equals 1, 3. The final result for the target bitmask, DP 7, is 1, 3, representing the smallest sufficient team. This team covers all required skills with minimal members. Edge cases to consider include scenarios where no people are available, redundant skills among individuals, or cases where it is impossible to cover all skills. For unsolvable cases, the algorithm should return an empty list. The solution for LeetCode problem number 1125, smallest sufficient team, uses a dynamic programming approach with bitmasks. Here's a breakdown of the implementation. 1. Skill mapping *. We start by mapping each required skill to a unique index using a dictionary. This allows us to efficiently represent the skills as a bitmask, where each bit corresponds to whether a skill is included. 2. Converting people's skills to bitmasks * for each person in the input, their skills are converted into a bitmask. Each skill in their list is checked against the skill to index map, and the corresponding bit is set in the bitmask. 3. Dynamic Programming Dictionary *. We use a dictionary DP where keys or skill sets represented as bit masks and values are the smallest team of people that cover those skills. Initially, DP starts with just the empty skill set, bitmask 0, mapped to an empty team. For iterating over people * for each person, we iterate over the current states in the DP dictionary. For each existing skill set, we calculate the new skill set obtained by including the current person's skills, using a bitwise OR operation. If the new skill set is not in DP or can be achieved with a smaller team, we update DP. 5. Result extraction *. The final result is stored in DP, 1n1, which represents the smallest team covering all required skills. Here, 1n1 is the bitmask where all n skills are covered. This algorithm is efficient because it leverages bitmasking to compactly represent skill sets and avoids redundant computations. The use of dynamic programming ensures that we always maintain the smallest team for each skill set, leading to optimal results. Here, we're implementing the solution to the smallest sufficient team problem in Java. The first step is to map each required skill to a unique index. We create a skill-to-index hash map, where each skill is associated with an integer value. This allows us to easily reference skills using bit manipulation later in the code. Next, we construct an array called peopleSkills, where each element represents the set of skills possessed by a person as a bitmask. For each person, we iterate through their list of skills, and if the skill exists in our skill-to-index map, we use a bitwise OR operation to update the bitmask for that person. This way, each person's skills are represented as a single integer, with each bit indicating whether they have a specific skill. Now, we initialize a dynamic programming table, DP, as a hash map. The key in this map represents the skill set, encoded as a bitmask, while the value is the list of indices of people required to achieve that skill set. We start by adding an entry for the empty skill set, represented by the key 0, with an empty team. Then, we iterate through the people skills array. If a person has no skills, we skip them, as they don't contribute to the solution. Next, we handle the dynamic programming transitions. We create a temporary copy of the current state of the DP map, which we will update as we process the current person's skills. For each existing skill set in DP, we calculate the new skill set that can be achieved by combining the current skill set with the skills of the current person. This is done using a bitwise OR operation. If the new skill set is not already in temp, or if the current team for this skill set can be improved by including the current person, we update temp. To do this, we create a new team by copying the current team and adding the index of the current person, then storing it in temp with the new skill set as the key. Once all possible transitions for the current person are evaluated, we update DP to reflect the changes in temp. After processing all people, the final skill set we need is represented by the bitmask, 1n1, where n is the number of required skills. We retrieve the team corresponding to this skill set from DP and convert it to an array of integers, which is returned as the result. This ensures that we find the smallest team capable of covering all required skills. To understand how the solution works, let's start with a basic example. Here, the required skills are Java and Python, and there are two people available, one knows Java and the other knows Python. First, we map each skill to an index, resulting in Java being 0 and Python being 1. Next, we convert the skill sets of each person into bitmasks. For instance, the first person knows Java, which corresponds to bit 0, so their bitmask is 1. Similarly, the second person knows Python, corresponding to bit 1, so their bitmask is 2. This gives us people_skills equals 1, 2. We then initialize a dictionary DP to track the smallest team for every skill set. Initially, it starts with 0, meaning no skills require no team. As we process each person, we update the dictionary. For example, when processing person 0, their skill set is combined with the current skill set, updating DP to include 1, 0. Continuing this for person 1, we update DP further, and eventually, we reach the final skill set where all required skills are covered. The result is the smallest team, 0, 1, which includes both people. Now, let's look at a slightly more complex example where some people have overlapping skills. Here, the required skills are Java, Python, and CPP, and the available people have varying combinations of these skills. First, we map the skills to indices. Java is 0, Python is 1, and CPP is 2. Then, we convert each person's skills into bitmasks. Person 0 knows Java and CPP, so their bitmask becomes 5, which is 1 of 4. Person 1 knows Python, so their bitmask is 2, and person 2 knows both Java and Python, resulting in a bitmask of 3. This gives us people_skills equals 5, 2, 3. Starting with dp equals 0, we process each person and update the dictionary. For instance, when adding person 0, we include a new entry for the skill set 5. Similarly, when processing person 1, we update dp to include the skill set 7, which is 5, 2. Person 2 adds further combinations, but we always ensure that only the smallest teams are tracked. In the end, the dictionary reflects all possible skill sets, and the smallest team covering all skills is 0, 1. In this next example, we introduce redundancy to demonstrate how the solution avoids unnecessary team members. The required skills remain the same, Java, Python, and CPP, but this time, one person alone has all the skills. After mapping the skills to indices, we convert each person's skills into bitmasks. Person 0 knows Java, so their bitmask is 1. Person 1 knows Python, with a bitmask of 2. Person 2 knows CPP, resulting in a bitmask of 4. Lastly, person 3 knows all 3 skills, so their bitmask is 7, which is 1, 2 of 4. Starting with dp equals 0, we process each person. As we add person 0, we update the dictionary to include the skill set 1. Person 1 adds skill set 2, and person 2 adds skill set 4, with combinations like 3, 5, and 6 being formed along the way. However, when processing person 3, we find that they alone can cover all skills with a skill set of 7. This leads to an update in dp, where the smallest team for skill set 7 becomes 3. This demonstrates how the algorithm naturally favors smaller teams, even when larger teams could achieve the same result. Finally, the output for this example is 3, indicating that person 3 alone is the optimal team. This is because they possess all the required skills, making it unnecessary to include any other team members. The solution effectively minimizes the team size by leveraging individuals who cover the most skills, and in this case, person 3's comprehensive skill set allowed us to achieve the goal with just one person. This completes the walkthrough for this example, showcasing how the algorithm handles redundancy and ensures the smallest sufficient team is selected. To analyze the time complexity of our solution, we break it down into 3 main steps. First, mapping skills to indices using the skill_to_index dictionary takes O(n), where n is the number of required skills, or len, our AQ_skills. This is because we simply iterate through the list of skills once to build the mapping. Next, we convert each person's skills into bitmasks. If there are p people and each person has at most k skills, iterating through the people list and processing their skills takes O(p*k). Since k is typically small and can be treated as a constant, this step simplifies to O(p). Finally, the dynamic programming table is updated by iterating through all subsets of skills. With 2 to the power of n possible skill combinations and p iterations for each person, the total operations for this step are O(p*2 to the power of n). Combining these steps, the dominant factor is the dynamic programming updates, giving the overall time complexity of O(p*2 to the power of n). Thus, the overall time complexity of our solution is O(p*2 to the power of n, dominated by the dynamic programming table updates. Now, let's consider the space complexity. First, mapping skills to indices requires O(n) space for the skill_to_index dictionary. Second, the people_skills list, which stores a bitmask for each person, requires O(p) space since there is one bitmask per person. Finally, the dp table is the largest contributor to space usage. It can store up to 2 to the power of n entries, one for each possible subset of skills. Each entry maps a bitmask to a team, which is stored as a list of indices. In the worst case, each team list could include all p people, leading to O(p*2 to the power of n space for the dp table. Combining these, the overall space complexity is O(p*2 to the power of n. To put this into perspective, let's compare the optimized approach to a brute force method. A naive solution would involve generating all possible subsets of people, which is 2 to the power of p subsets, and checking if each subset covers all required skills. For each subset, the skill coverage check would take p*n, leading to a total time complexity of 2 to the power of p times n. This approach becomes infeasible for large P due to the exponential growth in the number of subsets. In contrast, our dynamic programming-based solution reduces the number of combinations to consider from 2 to the power of p to 2 to the power of n by focusing on skill bit masks. Since the number of skills, n, is typically much smaller than the number of people, p, this optimization drastically improves performance and makes the problem solvable for practical input sizes. Finally, let's analyze the best, average, and worst cases for this solution. In the best case, all required skills are covered by a small subset of people, which means the DP table may not need to store all 2 to the power of n entries. While this can lead to faster computations in practice, the asymptotic complexity still remains p*2 to the power of n. In the worst case, where each person contributes unique skills, the DP table must store all 2 to the power of n entries, resulting in the maximum time and space usage of p*2 to the power of n. To prove this big O complexity, note that the DP table has at most 2 to the power of n entries, and each person updates these entries at most once. The time spent on each update is proportional to the team size, which is at most p, leading to p*2 to the power of n. Similarly, the space complexity is dominated by the DP table, which can store up to 2 to the power of n entries, each requiring p space for the team list. Thus, both time and space complexities are confirmed as p*2 to the power of n. When solving the smallest sufficient team problem, there are a few common pitfalls to be aware of. One major mistake is not using bit masking to represent skills efficiently. Without binary encoding, comparing subsets of skills directly can increase the complexity of your solution, especially as the input size grows. Another issue arises when relying on a purely greedy approach to select team members based on the number of skills they cover. While this can seem intuitive, it often fails to account for skill overlaps between individuals for the goal of minimizing the team size. Additionally, many solutions neglect the requirement to minimize the team size altogether. It's not enough to simply cover all the skills, you must also ensure that the team is as small as possible. Failing to consider this can lead to solutions that work for basic cases but fail more challenging ones. Another frequent issue is overlooking edge cases. For instance, scenarios where no team members are needed, such as when the skills list is empty, or when a person's skills are entirely redundant because they're already covered by others, need to be handled explicitly. Also, consider cases where a single person can satisfy all the required skills. These edge cases can easily trip up a solution if not accounted for. Additionally, inefficiencies in dynamic programming state transitions can cause problems. If you iterate over all subsets of skills at every step, the time complexity can quickly become exponential. Properly updating the DP state and focusing on efficient transitions is critical to keeping computations manageable. To succeed in interviews, it's important to understand key insights about this problem. Representing skills as a bit mask is fundamental for efficiency. For example, if there are m required skills, you can represent each skill set as an integer between 0 and 2 to the power of m1, which allows for compact and fast operations. This problem is essentially a variation of the set cover problem, which is NP-hard. Interviewers often expect you to use techniques like backtracking with pruning or dynamic programming with efficient state transitions to approximate solutions effectively. Optimization techniques, such as memoization, help reduce redundant computations and recursive solutions, while pruning and backtracking allows you to skip unnecessary recursion when the current team size is already larger than the best solution found so far. When explaining your approach, it's important to demonstrate an understanding of the trade-offs between brute force, greedy, and dynamic programming methods, as well as an awareness of the computational challenges involved. For additional practice, related problems like LeetCode 691, 1289, and 78 can help build the necessary skills. Different approaches can be used to solve this problem, each with its own trade-offs. A brute force approach involves generating all subsets of team members and checking which subsets cover all required skills. While simple to implement, this method is computationally expensive, with a time complexity of 2 to the power of n*m, where n is the number of people and m is the number of skills. Backtracking with pruning is another option. This method recursively selects team members while pruning paths where the current team size exceeds the smallest team found so far. While more efficient than brute force, this approach is still exponential in the worst case and requires careful pruning to be effective. A more sophisticated method involves dynamic programming with bit masking. Here, you use a DP array where each state represents the smallest team that can cover a specific skill set, and you update the state by iterating over people and their skill contributions. This approach is highly efficient, with a complexity of 2 to the power of m*n, but it requires a solid understanding of bit masking and state transitions. Another approach worth discussing is greedy approximation. In this method, you iteratively select the person who covers the most currently uncovered skills. While this approach is fast and simple, it doesn't guarantee the smallest team size, which makes it unsuitable for exact solutions. However, it can still be useful in scenarios where an approximate solution is acceptable, or as a starting point for understanding the problem structure. Balancing these trade-offs is key to selecting the right approach for the given constraints and requirements. Great job! We've covered the smallest sufficient team problem and learned how to use bit masking and dynamic programming effectively. Remember, mastering these techniques can boost your problem-solving skills for optimization challenges. Thanks for watching, and don't forget to stay curious and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!